Start over. Tonight we're going to talk about finite state machines, and that'll be the topic for tonight and the next lecture. And these will be on the final test for the class. We're not going to have a homework assignment on them, so the problems that I give you won't be very complicated problems. Okay, so first we need a definition, right? What's a finite state machine? And you cannot read that, can you? So a finite state machine is a picture with circles and lines, just like a graph. So it's a type of graph. But the nodes in the graph are called states. And the edges are called transitions. And they're directed. So the edges are directed. We use these for writing code. So when you want to design a program, one way to do it is to design a finite state machine. It's called finite because we have a countable or small finite number of states. It's a state machine because it works. We have a start state, and then we have transitions between the states, and we have an end state. And it's a machine because it works all by itself, and no one has to do anything to it. So let's do an example. So these are tied together very strongly with languages. And I'll show you how. So for example, let's say we label a start state like this. So we have a circle for a node, and we put a circle around it if it's a start state or an end state. Actually, let me make this end state so that I'm consistent with how everybody else does it. So here's an example. This will be our start state. You just label it because it has an empty arrow going into it. This will be our initial state, and we'll label it as 0, and 1 will be our final end state. And the language accepted by this finite state machine would be the language containing just the letter A, because it would be the only thing that this machine will accept and say yes. So if I get to this end state, the machine will say yes. So the output would be yes. If I don't ever get here, then that means I'm not in a state that accepts, like if a word is fed to this machine, like B, A, B, it won't take it. It won't even get out of the start state, because there's no arrows labeled with B
or else
or anything else. So if I get a B, I sort of go to nowhere. So if I wanted to really note that, so if I get anything else, B, I would put any other possible things I would expect and go to some other state, some other final state, and this would be an end state. This would be a second one where I would say no. So I could have final states that would make the machine stop, but my output would be no. So I don't actually accept that. So normally we don't necessarily draw these. So if we just want to describe what we do accept, we just draw that machine. If we want to describe things that we don't want to accept, then we do draw these. So the language here, so L, we would normally use a capital letter to denote the language that a finite state machine accepts. Here it would be A. Let's draw another one, very similar to that one. So here's another finite state machine. What's the language that this one accepts?
A.
A and AA and AAA. and any number of A's, right? So the language here is A followed by A star. What A star is any power, any positive, actually any non-negative number. So it can be 0. So the star stands for any integer starting with 0. And we also write, this A is here because we have to have at least one A. Another way to write that is A plus. So the plus is the positive numbers. So using the definition I've just given you, can everybody make a finite state machine that accepts their name? So let's use my name and make one for my name. It's kind of long, right? So we have a start state. It needs to have a T first, and then an I, and then an F, and then an F, an A, an N, and a Y. And we need to label our states. I could even label them with the letters that I've been getting. So this finite state machine accepts my name and nothing else. Because otherwise I get stuck in one of the states. Any questions about that so far? Yes.
Instead of FF, would we have put, the loop for F on itself?
That's a good question. If I had put on F1 maybe a loop that said F on it, or a little f, would that be okay instead of having F2 here?
No, you might misspell it.
So then I could have more than 2 Fs, right? Or I might have less than 2 Fs. So I could have, that would accept this. This is the language. If I mark out this state and put that transition there, this is the language here. So any number of Fs. So if I were to accept any number of Fs in my name, then that would be the finite state machine for my name. So the plus means at least one, and it means it could have as many as get put in. So let's get some examples of languages and then try to draw the machines for them. So what I'm going to, this star and plus, those are part of what's called a regular expression. So let me just give you what the definition of that is. So a regular expression is a way to express strings in a language. And it takes advantage of patterns. So it's going to be a rule for making words in the language. That's what regular expressions are rules to make words in a language. So we can use regular expressions for any kind of patterns that we want. So the things that we're going to use in a regular expression are going to be letters from the alphabet. So whatever kind of letters you want to accept in your language. We're going to have the operator plus, which means or, times, which is not written, it just means leave the letters in sequence. So it's like an and they have to be in the correct sequence. And then we know about the power. This is in the power. This is any non-negative integer. And a plus in the power is a positive integer. So these look a lot like our logical statements that we've used before, right? Except now we can, with these two things, we can have any number, we can repeat things any number of times that we want. So a regular expression, let's say R, so here's one that stands for Andy, and I can either use a capital letter or a lowercase letter in each case. So each of these is a choice, and I have to do 4 choices. So we could do a counting problem here, right? How many possible strings would there be? 8 possible. So in each of these, yeah, it's 2 to the 4th.
It's 16.
Yeah, so it's not 8, it's actually 16. 2 to the 4th, because I have 2 choices here, 2 choices there, 2 and 2, and they're all multiplied. Okay, so how do we draw a finite state machine for this? Each state represents getting part of the input that I want. So I have a start state always, right? And then I need to have a state that means I got the A, right? Either the little a or the big A.
The transition can be the little or the big A.
The transition can be labeled with all the acceptable inputs. So you can put each input and put a comma in between. Let's make that a little bigger for you. Oh, it looks different on screens. Okay, so now what?
Transition.
I need transitions for the rest of the letters, right? So now I need little n, capital N to get me to an N state, little d, capital D to get me to a D state, and little y, capital Y to get me to a Y state. And that will be the N state because I've spelled the whole name. So finite state machines can be used to represent regular expressions, but they can also be used to represent other things. So you could put other things on the transitions if you want to. So when you're making a finite state machine for a program, it's not necessarily reading strings. It's just that this is sort of the regular use of a finite state machine when you're describing them is to have them represent strings. But anything can go on the transitions. But states, that's when certain things have happened, and we want to differentiate among the states. So let's make a couple of more regular expressions, and then we'll make some finite state machines for other things.
So I can repeat however many times.
Okay. So here's another regular expression. This would be strings that start with any number of A or B's. Then it has a BA, and then it has at least one B, and then it can have any length of B's after that. So I could also describe this by saying any string in the language A, B star. So the whole language that I'm reducing this from, I'm going to assume that my alphabet is just A or B, any string that has A's and B's in it. So this regular expression is like a subset of that. So the English language is a subset of what, like big language? A plus B plus everything up to Z star, right?
No.
And we only accept the ones that make words that we recognize, right? So there's not a good regular expression for accepting English words, right? Because I don't accept everything that has two B's. There's no pattern to all the words in the English language that I could make one machine for. I could make a great big machine that describes all the words that are in Webster's or something. But that would really, really be complicated. Yes, you have a question.
When you start out with A or B star, you could have, star can be 0 because you really start out, if you have B and A as your first two inputs, does that automatically then make you expect the last B? You just ignore the first?
No. I could get BA, 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 a whole lot of them. So I'm just making these up, by the way, so we're going to have to make the finite state machine together. Okay? So yeah, we have to do something to figure out which BA are we on if we get a BA together. All right? So let's make the machine for that. Okay, so we have a start state. There's some cases that are going to be easy to figure out, right? If I get an A to begin with, I know I'm not at the BA part. Right? Actually, I don't actually have to describe everything. So here, I could stay in this state as long as I get A's and B's, any number of them. Then if I get a B, and this is the magical B, I can go to state 1.
But there's nothing determining which kind of B makes it magical.
We're going to talk about that in a second. Okay? And then I can get that magical A that goes right after it. And then I have to take at least one B, right? And this is an accepting state, and I can get as many more B's as I want.
So you're just making up states 1, 2, and 3.
Yes, I'm just labeling so that we differentiate them. Whenever you make a finite state machine, you do want to describe what the states stand for. In this case, it's for a string, so I don't actually have to describe what each state is for. If I'm using it to make a program, though, I want to describe what all the states mean. So one state might be, I've got the input of the person's name, and now I can go to the next part of the program. Like in your tutorials that you've done online, I have to get your name. Then after, I have to look up your data record. Then as long as that's okay, you get to do the rest of the lesson. If you're not one of my students, it'll kick you back out. Okay, so in this case, what someone said is that there's no way to tell that this is the magical B, right?
What's magical?
This is magical because it is the one that's right here. How am I supposed to know? There's no way to know from this machine that that's the one, right?
Any B will make
So
it
this one is
more
called non-deterministic. Because this jump right here, I don't know when it's going to happen. So something's called deterministic if you know when it's going to happen. It's called non-deterministic if you don't know when it's going to happen. So whenever it gets a B, it makes a choice. And this machine is assumed to make the right choice. It won't accept anything that isn't of this form, right? There's just no built-in guarantee that this thing is going to accept all of them, right? But it does. This represents that regular expression, but it's still a non-deterministic. You can represent any regular expression with a deterministic finite state machine. So we have to figure out how to do that. So how do we tell whether we've gotten the right BA or not? Any ideas about that? What do we have to know? We have to know, after we get that BA, do we get any more A's? Because we need to get BA, B, and then just B's, right? So what we would need is a state that has told me, okay, now I've got a BA, B. Do I get any more A's after that? If I do, I need to get kicked back to the start state, right? So that's what we need to build. So let's build a deterministic finite state machine for this problem. So we know we have a start state. And let's say that whenever we get a B, we need to go start checking whether it's the BA or not, right? So in A, as long as we get A's, we stay here. If I get a B, I need to start my little process of keeping track of what I get. Okay, so B says, okay, I might be on my way to getting that. If I get an A, I'm definitely on my way, right? Now, if I get more B's right here, I'm still on my way, right? I still could, that last B that I get might still be the one that starts it. So it's okay, I'm still in that waiting to see if I get the first A after the B, right? So I can get as many B's as I want right there and still sort of be in the same waiting state to see if I get A, B, and then just B's after that. If I get an A, then I know I've got a BA so far. All right? What if I get, we'll worry about what we do with the rest of it later. So now if I get my B, as long as I get just B's after this, we're good, right? So this is all right if I get here and I just keep getting B's. So if we want to make this a nice complete finite state machine, we specify what we do if we get an A or B at every single place, because that's all the letters that we could possibly get. So let's go back through and make sure we specify at every point what we do if we get each of the letters. So I've already done it in the start state. We know what we get if we get an A or a B. And here I know what I get if I get an A or a B. So now if I'm in state 2, the only thing I haven't figured out is what happens if I get an A. So that means I got a B, then an A, then another A, which means I'm still actually up in this A plus B star, right? So, and that means I'm still waiting to get a B, so actually I need to go back to which state? 0, because I'm still waiting to get the initial B. So in this state, I need to go here if I get an A. And the only thing left is if I'm in the 3 state and I get an A, then there's a problem, right? So where do I go? Back to 0, right? Back to 0 because that wasn't the BA. If I get any more A's, because I already got this, because that was in state 1, right? BA is state 2, right? BAB is state 3. And any more B's after that, I'm still in state 3. If I get any A's after that, then I'm no longer, I can't be any of these. I got to go back to this.
How do you know that you have to go back to that and that you might not be going back to state 2?
I can't go back to state 2 because state 2 means I've got a B, then an A.
But you might
Well,
have
that's
one.
actually true. You're right.
Yeah,
if I get an
I
A, I can go back to here. So if I just get B's after that, then I'm fine. So that's very good. So I got one B. If I get an A, that could be my first B, right? So what we just talked about right here was I could have gotten, state 2 means that I just got a B and then an A. State 3 means I just got an A then a B. So we're supposing that we got some B's here, and then what happens if we get an A? So now if you look at this, this looks like what state 2 looks like, right? Is that I get something and then I get a BA. That's what state 2 means. So going back to state 2 makes the most sense here.
If you get an A, you go back again.
And if I get another A, it gets shot back to the 0 state because I don't have BAB. So you can check these. You know, once you make one, you want to check it to make sure that it has, you know, that it accepts all the words that you want it to accept and doesn't accept any words you don't want it to. Right? So this lets me put any string of stuff on the front, any string of A's or B's, any combination of A's and B's. Yes?
Where is the state A plus B asterisk?
Where is the state? That's up front.
Oh, there's a 0 state.
Right. And then each state is sort of tacking the other one on front of it. So this is the 0 state, accounts for that. So this is a good way to check your diagram, and that is to make a list of what kinds of things you're accepting in that state. Right? So in state 1, I've got A plus B star plus getting one more B. In state 2, I've got A plus B star, and then 1 actually, it got one B, and then it can have any number of B's. So that's actually a B plus right there, because I can stay in state 1 by getting a bunch more B's.
Would you just back up a second for the state 0, for the star? What exactly does that star mean again?
Any number of them.
Gotcha. Thank you.
Right. And actually, I haven't proved right now that it's A plus B star. I haven't proved that. Well, we'll go back and verify that that's what it is. Okay, so this one we haven't verified. All this stuff, assuming that state 0 is correct, the rest of these are correct, right? A plus B star, then I get B plus, right? Then I get an A in state 2. That's the only way to get to state 2 is to do all those things. To do 0, 1 first. Or to do 3, so we also have to go back and check that one. Right? So plus whatever 3 does. So 3, we need to write down what that is all the stuff to get to 2, right? So we can write it like this to make sure we're checking everything correctly. Is all the stuff to get to 2 plus I get a B. Plus. B plus will keep me there. And that's it. So let me actually draw this over again because I assume that 0 was correct. So let's go back and do it, not assuming that anything is correct. So 3 was definitely 2B plus. So 0 is just nothing first is acceptable, and then any string of A's, right?
Or B.
Can't get any B's. The only way to get a B and go back, I can't get a B and go back to state 0.
Yeah. Okay.
Right, I have to have some kind of A's. So it's A star plus, I could have done state 2 plus an A, right? Whatever state 2's regular expression is, and then get an A after that, then that will put me in. And actually, an A plus will keep me in state 1. So what you want to do when you make this table is describe all the possible strings that could get you into that state. So either I got here with either nothing or a series of A's, or else I got to state 2 and then got any number of A's after that, 1A plus any more. Right? Okay, now state 1 is anything that gets me into state 0 plus putting a B after it, and then putting any number of B's after that. So B plus is going to be state 1. Okay, now state 2 can be gotten at from doing state 1 and then getting an A, or we can get to state 3 and get an A. And the only way to get to state 3 was going through 2 and then doing B plus. So this is actually what the strings are for these. And we'd have to go back and verify that 0 actually is A plus B star. And then the rest of these should be correct. Okay, so let's go back and plug in everything that we can. Just sort of, because this is kind of recursive like this, right? Through the states. So let's try to make it not recursive. So we can expand each one of these, and I'm just trying to figure out what order I want to do them. So 2 seems to be like the one we need to figure out. Right? If I put these 2 together, though, that's actually nice, because this can be written as 1 plus 3 and then getting an A. So you definitely can't get to 2 without getting an A, right?
Yeah.
That makes it a little bit simpler to read. And then if I plug in for 3, let's think for 2. And if we look, 1 and 3 have something in common, right? They have at least one B on the end, a string of at least one B and lots of B's. So that's good. We're getting it closer to what we want for these regular expressions, right? So let's work with this. All right, so now we have 1 and 3 end in a B plus. So let's replace 1 in all of this. So 2 is, if we replace 1 with 0 B plus, that's going to be 0.
Move over a little bit.
Sorry. We're going to be 0 B plus if we replace the 1 in this 2. Actually, let's leave 2 being recursive instead of 3. Okay, so instead of 3, I'm going to go ahead and put that 2B plus back in there. Just looks a little easier to deal with to me, because then these both have B pluses on them and I can factor them out. So now 2 is written pretty easily recursively as either the start state or 2, and then I have to get a string of B's and then an A after it. Okay. Let's see, what else do we want to do with this? So let's look back at our diagram and see how does that correspond with what we wanted.
Excuse me.
Yes.
I have a question about over there. It's on the bottom it says 2 equals 0b plus 2b plus. That's 2b plus that may not be the same plus. For example, one of the b plus maybe b4, another should be b maybe b8, b7, something like that. Can we take b plus out at the
answer is yes, because neither one of these actually stands for right now plugging in any number. So this plus doesn't stand for plugging in a 3, and this doesn't stand for plugging in a 4. It stands for any number of b's as long as it's at least 1. So it's okay to factor it out, because if I see a string that has 4 b's, if I'm in state 0 and then I get 4 b's and then get an A, this describes it just as well as being in state 2 and getting 3 b's and then getting an A.
Okay.
So it's okay, I can factor it out, because I haven't, that's a question of like instantiation, right? So I haven't actually said what the plus is at any point when I make these expressions. So it's okay to factor them out, because I never said that it had to be 2 or 3 or 5 or whatever. Does that make sense to everybody? Is it all right? Okay. So we can move a B plus around we can move B stars anywhere we want. So it just means, since this means at least one B followed by any number of B's, it actually works for both of those. Writing B plus once is the same as writing it next to each of those other ones. Okay, so let's rewrite our little diagram of what each of these stands for. Okay, I'm going to write these again. We've got now that 2 is either 0 or 2, B plus A. And now for 3 we have, if we just go back to that, it's 2 and a B plus. So if we want to prove that this represents the language that we want to show that 2 is equivalent to getting A plus B star, getting BA. So now we have that it's BA, so we just have to show that 0 plus 2 is A plus B star. Does that make sense to everybody?
2 contains 2.
Right, 2 is recursive.
Yeah, okay.
It's any sequence of stuff that would be accepted by 0 or 2, followed by at least one B, followed by an A. That's what 2 stands for. Anything that's accepted by 0 or 2, followed by a B and an A.
So now you have to prove that substitution works.
We have to prove that the stuff that is accepted by either 0 or 2 is A plus B star. Okay? So that's what we want to prove. Let's write that down. So in order to prove that 3, since that's our accepting state, we want to prove that 3 stands for A plus B star, BA, and then B plus. We already have the B plus on the 3, right? And we already have that 2 ends in B plus A.
So shouldn't there be a plus on that B? Yes.
So the plus, we can actually break up a plus always into a B star B or a B, B star. So actually 2 we could rewrite as B star B, BA, right? So 2 can be written like this. So I might not get any B's, then I definitely get one B and then one A. So now we've already got the BAB plus for 3. So now we just have to show that these two states together plus a B star on the end, because this is what 2 is right here, we have to show that that is equal to A plus B star. Because we've already got our BAB plus. So what we could do is we could suppose that we have any string that's in A plus B star and show that it's accepted by 0 plus either 0 or 2 state. Okay, so let's suppose we have a string x. And x is in A plus B star. We can do an inductive proof on this. And a lot of times you have to do inductive proofs on these because you need to know the length of the string so you know when you're done proving it. Right? So let's do an inductive proof.
Question before.
Yes.
State 2 is state 0 plus 2 B star BA. How did you change that to B star only?
The B plus, if you look here, we have a B plus.
Yes.
That means at least one B, and it could have any number of B's. B star is 0 or more B's, right?
Okay.
So B plus equals B star B. That's all I did.
All right.
It also equals B, B star, right? So those are all equal, and that's what I did because I knew I needed one of those B's for the BA, B plus for my string, right? Good. So we want to prove that that's logically 0 plus 2 B star is logically equivalent to A plus B star with parentheses around the A plus B. So we're going to do it by induction. We're going to assume that if we have a string in A plus B star that it can be accepted by our states like this, 0 plus 2 B star. Okay, we're going to do induction on the length of x. Where x is a string in A plus B star. Okay, so the basis is what? What's the minimum length of a string? 0. So the length of x is 0, then x is equal to the empty string, right? The empty string is usually denoted by epsilon. And that was accepted by the 0 state, right? Because A star was accepted. Right? So all we're trying to prove is that x has to be in zero or 2 B star. And since it's the empty string, it's in the 0 state because A star is in there, right? A star has the empty string in it, and B star has the empty string. Empty string put with the empty string tacked on the end is still the empty string, so x is in there. So we assume if the length of x is equal to n, that x is in 0 plus 2 B star. Sorry, let me make this wider. Make sense? If the length of x is n, then it's in the set that we want it in. Now if we want to prove that if the length of x is n plus 1, let's just say, we'll just call it y. Okay, we need to add a character, right? Because it can't be x if we increase the length by 1. So we want to prove that XA and XB are both n. Because those are the only other letters I can add to it, either A or B. And that's the only way to make it longer by 1 letter.
Not x plus 1.
No, it's not x plus 1 because x is a string, and I can't add numbers to a string.
The size is increased by 1.
The size increases by 1. So what we normally write actually in a proof like this is assume that if W has length n plus 1, then prove W is in here. But then we can, usually I just skipped a step here, so that it implies that W is in there. Okay, but any W can be written as a string of length n plus a character on the end, right? Or a character on the beginning. So I might actually need to do that. So we'll see what we need to do. Okay, if it's ends in B, and X was already in this language, then XB is still in that language, right? So that's good. That helps, right? So if, let's say if W equals XB, so and X, the length of X is n, we know by induction that X is in 0 plus 2B star. And just because we have a B star there, then that implies that W is also in 0 plus 2B star. So ending in a B is great. So the only problem is if we end in A. Then actually we don't actually want to do this case. We want to prove that it had to start in some other way that makes us still be in the set, right? So if W equals XA, then we need to do something else. In that case, we're going to break it down into 2 cases where it's actually a string of length n that starts with A or one that starts with B. Right? Because all the strings have to start with either A or B. So we're not going to look at the end letter anymore because B star doesn't help us. So then W is going to be equal to AY or BY. Right? It's one of those two. And now Y is of length n. So instead of trying to separate out the last character, I'll separate out the first character. And now the length of Y is equal to n. So by induction, we know that Y is in the language that we want. So we know Y is in 0 plus 2B star. So now we have to look back at the definitions of 0 and 2. So now if W is equal to AY, we have that 0 is equal to A star plus 2A plus, and 2, let's see, I have to look at this. So what are your ideas? Nobody has an idea? What are we trying to show? Does everybody know?
I thought we wanted to show that A plus B star is in state 0, is the beginning.
But we're partway through the proof, so there's something we want to show now, right? Okay. If we don't understand the proof so far, we need to go back. Okay, we have a basis. So we're proving that these two languages are the same, right? So if I have any string in A plus B star, it's got to be in here. I have to do it by induction on the length of the string, because that's the only thing that I know how to use for a string. I have to look at parts of it, and I need to know how long it is. Okay, so basis length equals 0. That's the easiest case. If the length equals 0, I can represent it by being in the 0 state and doing B star. That's fine. That empty string is in that. I assume that if I have a length n string, that I'm already in the language I want it in, 0 plus 2 B star. Now I want to prove, and maybe that was my mistake by not writing it better. So prove. Let's do it again. Prove if the length of W is n plus 1, then we want to prove that W is in 0 plus 2 B star. And I'm not going to put circles around those because it just takes longer, makes it harder to read. So if the length is n plus 1, then I want it to be in that. And I have to use the fact that any string of length n is already in that language. Okay, so in one case, so I know either W is equal to some XA or it's equal to XB, right? Where X is a string in AB star, A plus B star, of length n. That makes sense, right? Because in order to make a string with n plus 1 characters, I have to have a string with n characters and then put another letter on the end. And the only letters in my alphabet are A and D. So those are the only two ways to get a string of length n plus 1. Now we know if we end with a B, that we can take the B off and still be in the language. Right? We can add any B's. If we have an X of length n, we can add any number of B's on it because our state ends in B star. Right? So case 1, W equals XB. Right? We know by induction, since the length of X is n, that implies that X is in 0 plus 2 B star. If X is in that, then XB has to be in that, because you can add any B's onto anything and still stay in this language. So that implies that XB is in 0 plus 2 B star. So now we know W is in there. The nice thing about induction is we haven't had to unroll what 0 and 2 are yet. We only have to do it in the very last part, where it gets the hardest, right? So that's going to be the next part. And that's where you started getting confused. So here, we're still fine. We know we're looking at a string of length n plus 1, and that we can break it into pieces, one character plus n other characters. And we want to use our inductive step to know something about those n characters. Now we have to deal with the problem of, what if W ends in A? Okay, let's try that. So I haven't done this proof before class. I wanted to do it together with you, so let's work together to get the next part. So case 2, W is equal to XA. Now we have to look back at our states, right? So what does 0 look like, and what does 2 look like? 0 was, let's write this on the sheet, A star plus 2 A plus. And 2 was here, let me write this on another line because it's long, right? 2 was 0 plus 2 followed by B star BA. So actually ending in an A doesn't look too bad, does it? because the B star could have nothing in it, right?
Mm-hmm.
For W to be in there. And we just have to show that if we take an A off, we're still in there. Or we might have to break it up another way. So when you're doing these proofs, you know what your goal is. You just might have to try a few different things. So here we know what 0 and 2 are. The problem with taking this A off and then hoping that X is, we know that X is in the language, and adding an A on, we have to see if it's still in the language. So let's suppose that X was in the language. And let's see if adding an A on it is going to still help us. Okay? So if X is in the language here, 0 plus 2B star, and we add an A on, what I'm trying to get at is we might not be in the language if we take an A off of W. Right? Because this has an A plus, that has an A star, might not have any A's in there. And taking A off here, we're not in state 2 anymore.
So would you have to do a mini proof by contradiction inside case 2?
No, I might split it up to looking at the first character. Yes?
Oh, I was just going to say if you go ahead and add 0 and 2, you end up with A star or 2A plus or, and then everything in front of it with A.
Oh, okay.
So,
So
that
0
you have
plus
an A
2.
on all terms.
So 0 plus 2 is A star plus 2A plus, right?
Mm-hmm.
Plus 0 plus 2
Yeah.
itself.
Well, I didn't know if that
That's
would
fine.
help.
That's fine. It just looks a little funny. B plus A, right? Because that B star B is B plus.
All those terms end in A.
Okay, so this is like a sort of a new state. Like if we could have a state in our diagram that was labeled 0 plus 2. So in all of these, anything that ends in an A, you're right, can be in here. So the next thing to do is to see if X is in there and I add an A on there, am I still going to be in there? So if X were somehow in here, that's fine, right? Adding an A on there is fine. If X was in here, adding an A is fine. The only problem is if I'm in this one, right?
But it's recursive, that part.
It's recursive, but it still has to end with B plus A. But the thing is, the cool thing is that our language actually is 0 plus 2 followed by a B star. So that doesn't actually help in that case. So B star is fine. Sorry. I thought it was going to help, but it doesn't. Okay, so that did help us look at it a little bit. So let's try what I was going to do before. Let's say W is AY or W is BY. And Y is in our language 0 plus 2 B star.
Would that be
Okay.
X equals AY or BY?
No, W was our, I'm not breaking X down any further. I'm just switching it. So Y actually ends in an A, right? So we're not actually going to use the B star. Because we know we're not using the B star. So we had to be either in the 0 state or the 2 state. Okay, so we want to show, we know that Y is in here, and we actually know it doesn't have a B star on there. And we want to show that AY is in there. So A hate to like try to think through this with you guys like waiting for me. So
I'm just curious about the recursion part. So would you only really have to prove that A exists inside of state 0 since 0 is included in state 2?
that's right.
Okay. So,
Right. If I just have to show that I can represent it, that I just have to show that W can be written some way by expanding out the 0 or 2. Right? That it's somewhere in there. I don't have to prove that everything in there is something else. Oh, that was weird.
So could you get it just from the definition of state 0?
Can I get it from the definition of state 0?
Just A or B?
What I want to do is show that if Y is in this, if I put an A on the front, then it's still in there. That's what I want to do. Or if I put a B on the front, it's still in there.
Okay.
Okay, so if Y is in there, if Y is in state 0, so let's do this. So if Y is in 0, adding an A on the front
It's no problem.
is no problem, right? Because then I'm still in 0 plus 2, which is what I wanted. If Y is in state 2, we have to see what happens with AY. So in state 2, that was 0 plus 2, B star VA. So adding a 0, an A on the front is fine because it's got a 0 plus 2 on there. So it just ends like this, and I can add as any number of A's on there. Okay, so we're okay. So AY is still in there because you know what I'd like to do actually is finish this proof for you guys and show it to you next time because it's a little bit complicated because I still have more cases to do. And writing this down. Remember what we said a proof is? It's like a convincing argument to the person reading it. Okay, so I want to make it convincing. I don't want to just write it down here and have you go, oh yeah, that looks good. But it looks like we're going to get it, right? We just have to make sure that we get the right character taken off the front. So you have the idea now to show that two languages are the same. How do you do it? So if someone asks you to prove that two languages are the same, what would you do?
Come back to you.
Like just a induction. So you would say create a basis where they were the same, and then say they're same for length n plus 1.
Well, equals, languages are sets, right? So they're sets of strings. That's what languages are. So if I want to prove two sets are equal, what do I need to do? Right, that proves a subset relation, right? So I need to prove two things. I need to prove L1 is a subset of L2. And I need to prove that L2 is a subset of L1. And once I've done that, then I'm done, right? So if I want to prove, so say I just wanted to prove this first one, and you can do sort of the same sort of thing, vice versa. So if I want to prove that L1 is a subset of L2, I assume that I have a random string X in L1, and any of those, that has to be true that if X is in L1, then it's in L2, and that's a proof that L1 is a subset of L2. If I get a random string, and if it's in L1, then it has to be in L2. So this is what I'm proving. I'm proving this implication right here. So I want to do it by induction on the length of X. So you're always going to have a basis where the length is 0, or else whatever the minimum length of a string is in L1. And then I'll assume that if I have X in L1, then it must also be in L2. And then I have to show that if I have a string of length n plus 1, in L1, then it must also be in L2. So let me write that little outline. So this is going to be really useful for you in your next class, and also if you take, what's that class? 333, Finite Automata, Regular Expressions, Languages. That's what this whole class is going to be about. You'll be doing proofs like this all the time. So if I want to prove L1 is a subset of L2, then we do it by induction. On the length of a string in L1. So basis, length of x equals 0, or whatever your minimum is. That's just L1 right there. So you just have to show that if x is in L1, that implies that x is in L2. So you'll just have to show that your basis string is in both of the languages. So in this case, if that's your minimum string, you show it's in that and in L2. So in L1 and in L2. Assume if the length of a string is n and x is in L1, then that logically implies that x is in L2. You want to prove if the length of w is n plus 1 and w is in L1, then you want to prove that implies that w is in L2. And you'll use your assume statement to do that. So this is a generic outline for proving that one language is a subset of another. So assume you have a string in the language, and by induction on the length of the string, you show first that the very smallest string is in both of them. Then if you have a string of length n in the first one, that it has to be in the second one, you assume that. And then you show that if you have a length n plus 1 string in the first one, that it also has to be in the second one. So that's the structure of an inductive proof to show that one language is a subset of another. Because you can have multiple ways to write. Like you could write regular expressions even differently for the same language.
Right after the word show, what is that symbol?
That's an epsilon. It just means the empty string.
Okay.
Sorry, that's the empty string. That whatever your minimum is, so if your length is 0, it happens to be epsilon. So whatever your min string is, you have to show that it's in both of them. So if the empty string's not in both, you have to show whatever your basis smallest string is, you have to show it's in both. So whatever, you can just use this to represent the smallest string. But if you see it in a book that's doing this stuff, it's gonna stand for the empty string. So this is just like any other induction proof that you've ever done. It's just that breaking a string, breaking the last character off or the first character off is the trick between here and here. So the trick is to break a character off and put it back on. So you can use the assume statement.
I have a question.
Yeah.
Would it be an acceptable proof when you're looking to prove languages equivalent? Could you use the matrices so that if you said that if you could create a matrix, I guess you wouldn't know necessarily how long your string is though. Never mind.
That was a good question. You can have...
And if it was,
you could have a matrix with a cross product and put ones where you had strings that were in the language and zeros otherwise, but you'd have an infinite matrix, so that would be kind of hard to do. So it would be hard.
Take a long time anyway.
Right, so an induction proof on the length of the string is the way to go on that.
Yeah.
Okay, so in designing programs, so we have languages, and those are represented by finite state machines. So you can always draw a deterministic finite state machine for a regular expression. And you can use non-deterministic ones too. So you can have a finite state machine that just sometimes randomly jumps from one state to another. That's another non-deterministic finite state machine, and you'll talk about that in later classes. I just wanted you to know that they exist, because you can always have transitions that happen whenever they feel like it. But if you want a deterministic one, which is what you want to program, right? You don't want your program to randomly decide to now start saying no when people offer you money for the product you're trying to sell. like Coke machines do, right? So you want to design your things better than that so that you know what's going to happen no matter what the input is. So if you design a finite state machine, like if you make a design for a program and you find out that it's non-deterministic, what do you need to do? You need to make it deterministic, right? Because you need to know what happens in your programs. So one thing you might do when you're designing a program is you might decide what states are, like in the grocery store. Say you're designing a finite state machine for your cash register, right? You start at a start state, and then you get a customer, right? So when things happen, you want to change states. So I'm just making up a little problem, and then you would build your code based on this. And you would check it based on this too. So some cool things that in computer science have, like if you've built a finite state machine for your program, you can check whether it's correct, check whether the code actually matches your finite state machine or not. And there's some neat stuff doing that. And there's lots of research in those areas too, like taking a piece of code and making a finite state machine for it. Or vice versa, making a finite state machine and then making a piece of code that matches with it. Right, so say this is, your little guy is standing at the cash register. Then you get a customer. So we're going to assume that the cash register is already on. And that he's in the state of unloading the cart, right? And he gets one item. And he scans it, right? So we're unloading the cart. Actually, we could actually just go, we want to minimize the number of states, by the way, because you want to program less. So if you can do the same thing in one state, you want to do it. So we keep scanning items, and as I scan an item, this is add the price to the total, right? So this might be what your design sheet looks like while you're working on it. Add the price to the total. And then when I get the last item, then I get to the state where I need to take money from the customer, right? So this needs to display the total. And the customer needs to pay, right? So now you get money, and then you give a receipt, right? So in this state would be the final state, and I give a receipt in this state. So this is a really simple example of designing my cash register. Because I might also want what? Might get the last item, and then they might say, and you display the total, and they say, oh, I also want to get this. Right? So you might actually get another item there. But having a diagram, this is a nice way to say, hey, did I cover everything that I wanted to? And you could also, the more complicated the problem, the more you might actually want to make a little diagram that says what each state actually represents. What do I want to have done by that state? How can I go from one state to another? And that's what a finite state machine is useful for, is sort of narrowing your problem down into a model. That's what a finite state machine is, a model of a problem or a model of a process. And that's what most of computer science is figuring out what is the problem, what is the model for the problem. That's more than half of solving the problem if you can actually write it down and make a picture of it. Because now this isn't so hard to code, right? If someone comes to you and says, this is the model I want and nobody will ever do anything different, then you can code this no problem. But the other problem being a programmer is they will probably also get mad at you if they pay you $20,000 for a piece of code and something happens that they didn't anticipate. So another part of your job is to actually think about their requirements and see that they meet what they give you. Okay, we'll see you next time. I will go back through that example and show the whole proof for that. And we'll finish up on finite state machines and languages and expressions.